All right, in this video, we are going to be talking about Euclid's axioms and his postulates. So these are the assumptions that Euclid makes to eventually build the entire system of Euclidean geometry. And Euclidean geometry is geometry that deals with flat surfaces or planes. And he defines a whole series of things, including a plane. We will get into those. But first, we just want to set the foundation using these basic assumptions and then conclude everything else that follows in geometry. Before jumping into this, I just want to describe what I want you to be doing right now. So as you're watching the video, you should be completing this, your copy of this, with his axioms and postulates. Eventually, you'll turn that into our Google Classroom whenever you're done with just this set, and then I will give it back to you and we'll continue working on this as we build up geometry and develop more theorems. So if you need to pause the video and type yours out on your set, that's fine. If you have a second monitor, that might be easier. If you're able to split the screen, that might also work. However you need to manage this, that's perfectly okay, but you should also be filling out your copy and then submitting that whenever you finish. So let's jump into these. Euclid's axioms are the accepted truths that cross over branches of math. They don't just apply to Euclidean geometry, they are true across every branch of math, which is actually why you probably heard of some of them last year, like this first one. Things which are equal to the same thing are equal to one another. Actually, that's just another way to say the transitive property. He says them in very basic language, just something that's equal to something else. Two things that are equal to something else are also equal to each other. The algebraic way to put this is that if A equals B and B equals C, then A equals C. That is the transitive property. We can basically just jump over B. If we know that A equals B and C equals B, well, then we know that these two also have to be the same. This might seem overly simple, but we need to start out simple so that we can build up. We need to accept certain really, really simple truths so that we're able to get to more complex ideas. If equals are added to equals, the wholes are equal. You learned this last year as the addition property of equality, or APO. I'm just going to show an example of that. Actually, let's start out with the exact same thing. If A equals B, what this is saying, if equals are added to equals, the equals that he's talking about here is this A equals B. The equals that he's talking about here is adding the same thing to both sides. The equal value is added to something that's already equal. The new whole that's created from that, A plus C, is equal to the other whole created from this, B plus C. You might see where the next one's going. I'm going to erase that just so I have room. But it's the exact opposite. Maybe not opposite, it's a really similar idea. I wish that would get out of the way though. Okay, well, I'm just going to say what this is. Maybe I'll write it out there. Yeah, there we go. Oh, well. If equals are subtracted from equals, so I'm going to start out with that same first statement. If A equals B, and I take the same thing away from both sides. I take away C from this, I take away C from that side. They will remain equal. The remainders, A minus C and B minus C, are still equal to each other. And that's ESPO, the subtraction property of equality. So as long as we do the same thing on both sides of the equation, it doesn't change the equation. The equation still remains true. All right, Euclid's fourth axiom. Things which coincide with one another are equal to one another. This is maybe the most self-explanatory one, but it needs to be said, especially when we're using proofs. The reflexive property, which basically says that something is equal to itself. An algebraic way to say that is that A equals A, which seems like a pointless statement. But in geometry, when you have a picture, actually, let me draw that. Let's say I have that triangle, and it's split in the middle by an altitude. This green side, maybe I should color coordinate, that green side is a part of this blue triangle, and it's a part of the red triangle. We can assume that it is equal to itself, and I know that seems really, really silly to even say, but it does need to be said as you're going through a proof. You need to say that because it's a part of this triangle and it's a part of this triangle, it is actually the exact same side and therefore the exact same measurement, or sometimes it's going to be an angle, but it is the same in the left triangle and the right triangle in this picture. The last one is the whole is greater than the part, which is really setting us up to eventually build to the whole. So let me show that with maybe a line segment, actually. That might be the easiest way. All right, so if I split this line segment, I have this length, let's call it x, and I have this shorter length, which is a part, that's the part. I'm going to call that y, the whole, which is x. I know that y is shorter than x. Again, that seems so obvious, but what it's really building up to is that I can take another number, let's call that z, and add it to y. I can take another measurement, add it to y, and build it up to make x. There are other conclusions that we can make from this, but that is the most basic one, that eventually we can take y, add something to it, and build up to the whole, because the whole is greater than the part. All right, now Euclid's postulates specifically apply to the field of Euclidean geometry. So the axioms span across all math. These are particularly applied to Euclidean geometry. A straight line can be drawn from any point to any other point. Again, that seems self-explanatory because most of the geometry that you've seen before has been on flat surfaces, but actually there are situations in other geometries where this is not true. That is why we actually start with these just really, really simple foundations for Euclidean geometry. A straight line can be extended continuously in a straight line. So actually these kind of follow one another. I have a point here, I have a point here. I know I can draw a straight line between those because actually that is the assumption. I am assuming that this postulate is true. I can draw a straight line between those two. His second postulate says that I can continue that continuously in that straight line. So this is really from here to there is called a line segment. The continuous line, actually I don't even need to say continuous line. Line is implying that it's continuous or infinite in both directions. A line segment has endpoints like that and that. We are going to get into a lot of these definitions later, so if I'm saying something that's not totally clear, that's okay. I think some of these definitions, endpoint, I think you guys can understand on your own, but we will actually get into a more formal definition of those. All right. Don't worry about that picture at the bottom. I'm going to explain what that means in a second. A circle can be described by a center and a distance. Really all he's saying is that that is all we need to describe a circle. A circle is completely defined by those two things, a center and a distance. That distance will be the radius or the diameter. Those are actually the same thing. Not the same thing, but they describe the same quality of a circle. Oops, I didn't really mean to do that. All right, number 4, all right angles are equal to one another. And again, that seems very straightforward. Obviously, they're all going to be 90 degrees, but it's actually more complicated than that. Hyperbolic and elliptical geometry, which is what we're showing there and here, right angles are not all actually the same. So in this, you can imagine if you were to extend this, that is a terrible circle, but let's pretend that's a circle. This right angle starts bending away from a 90-degree angle. It's actually not a 90-degree angle. Same thing with elliptical. So this is like on the surface of a globe. This is within the surface of a globe. That's what elliptical geometry is really talking about. If you're inside of a ball, the angle starts bending back towards, let's say, less than 90 degrees, although it actually is still a 90-degree angle. There is still a right angle here in elliptical geometry. So when you go across branches of geometry, not all right angles are equal to each other. But for our sake, all right angles are congruent to each other. And that's what we're actually seeing there. That is a true right angle in Euclidean geometry. All right, the last one is very wordy, but it's also a really simple idea. Oops. All right, if a line segment intersects two straight lines forming two interior angles on the same side which have a sum less than two right angles, then the two lines, if extended indefinitely, meet on that side which the angle sum is less than two right angles. That is the wordiest way to say a triangle will be formed when we don't have two right angles. So I'm going to draw that picture, and I'm going to slowly go through that. So we have a line segment that intersects two straight lines. All right, so I got one straight line. I have a second straight line. And then I have a line segment that intersects those two. It hits both of those. This is my segment. Let's call this line L and this line M. And as long as we're naming things, let's call this line segment N. So N is intersecting with L and M. So we have that part, we have that part, and this forms two interior angles on the same side. So that part is described by this angle and this angle. Those are my two interior angles on the same side, and they have a sum that's less than two right angles. So basically, that's less than 90 degrees. That's less than 90 degrees. Actually, let's label those two. X and Y. They don't both need to be less than 90, but in this case, they both are. They are less than 90 degrees. Really, what he's saying is that they add up to something that's less than 180. In this case, they actually happen to be true for this, but that part is not implied here. This is really the implication that X plus Y is less than 180. Then these two lines, this line L and this line M, if extended indefinitely, like all lines really are, meet on the side which has this sum that's less than 180 degrees. It meets in this picture, on the right side, on the same side where those two angles are formed. It eventually leads us to parallel lines, and even more specifically, that there is only one set of parallel lines that pass through a point and a given line. We will get to that and why that implication follows, but for right now, basically all that he's saying is that if this plus this is less than 180, this will form a triangle, and that intersection will be on the same side as those two angles. All right, so again, if you didn't quite get everything done from there, you can always go back into the video and copy things down that you need. If you need any help, please let me know. You can email me at any time.